Good day, everyone, especially to Ma'am Barbara and Dile. This is the video demonstration of our project entitled 2-bit by 2-bit binary multiplier. This is in partial fulfillment of the requirements for the subject CPE C301 Logic, Circuits, and Design. And this is presented by Group 2. The members are Celine Celestia, Maria Pauline Santo, Justin Angela Cristobal, Maria Zaret Samas, and yours truly, Angeline Imosino. So for the introduction, the project is focused on the design and implementation of a 2 by 2 binary multiplier. A binary multiplier is a digital circuit that performs the multiplication of two binary numbers. It is commonly used in various computing and electronic devices such as computers, calculators, and other electronic systems. In this project, the 2 by 2 binary multiplier is implemented using only four AND gates and two half adders. The AND gates are used to perform the logical AND operation on the input binary numbers, while the half adders are used to perform the half adder operation on the input of the AND gate. This allows the circuit to perform the multiplication of the input binary numbers and generate the correct output result.
Now we will be discussing the logic diagram of a 2 by 2 binary multiplier. In this discussion, we will be discussing how to use four AND gates and two half adders to multiply two 2-bit binary numbers, A and B. The inputs of our multiplier will be the 2-bit binary numbers A0, A1, B0, and B1. Before we dive into the details of our logic diagram, let's first quickly review some basic concepts in binary arithmetic. Multiplication is performed by adding the multiplicand to itself a number of times equal to the value of the multiplier. For example, to multiply two one binary numbers, we can simply add the two numbers together. However, when multiplying larger binary numbers, we need to use more complex logic circuits. Now let us discuss the half adders. One common building block for binary multiplication circuit is the half adder. A half adder takes in two inputs, A and B, and produces two outputs, a sum output S and a carry output C. The sum output is simply the XOR of A and B, while the carry output is the AND of A and B. Then for the AND gates, another important component in our logic diagram will be AND gates, and an AND gate takes in two or more inputs and produces an output of 1 only if all of its inputs are 1. If any of its inputs are 0, the output will be 0. Now that we have a basic understanding of half adders and AND gates, let's discuss how we can use these building blocks to create a logic diagram for a 2 by 2 binary multiplier. To start, we will use four AND gates and calculate the uh, partial products of our multiplication. The partial products are simply the AND of each bit of the multiplier with each bit of the multiplicand. In our case, this means we'll have four AND gates, each taking in one of the inputs A0, A1, B0, and B1. Next, we will use two half adders to sum up the partial products and produce our final result. The first half adder will take in the outputs of the first and third AND gates as inputs. The second AND gate will be the first output of our multiplier, labeled as C0. Since the sum output of the first half adder will be the second output of our multiplier labeled as C1, the second half adder will take in the carry output of the first half adder and fourth AND gates as inputs. The sum outputs of the second half adder will be the third output labeled as C2, and the carry output will be the fourth output labeled as C3. And that's it. By using four AND gates and two half adders, we can create a logic diagram for a 2 by 2 binary multiplier. I hope this discussion has been helpful in understanding how the circuit works. Thank you.
Here we have the components of the 2-bit by 2-bit binary multiplier. Next. First, we have the dip switch 2-pin. A 2-pin dip switch is a type of small rectangular switch with 2 pins that can be used to control the flow of electricity in a circuit. It is commonly used in electronic devices to enable or disable certain features or functions. The switch can be easily flipped with a small tool or a fingernail to change its position, allowing for quick and easy adjustments to the circuit. Next. Here we have figure 4.7 segment display with its pin configuration or the 7-segment cathode. Next. A 7-segment display is a common type of electronic display used to display decimal numerals and other characters. It consists of 7 individual LED segments arranged in a rectangular or diagonal pattern to form the numerals 0 to 9 and some letters. In a common cathode 7-segment display, the cathodes of each LED segment are connected together and are controlled by a single negative voltage. This allows the segments to be lit by applying a positive voltage to the corresponding anode. Next. Figure 5, 7447 pinout, or what we call the 7447 BCD to 7-segment decoder. Next. A 7447 BCD to 7-segment decoder is a digital circuit that converts a 4-bit binary coded decimal or BCD input into the corresponding 7-segment display output. This allows a BCD value to be displayed on a 7-segment LED or LCD display. The 7447 decoder has 4 BCD inputs, A, B, C, and D, and 7 output lines, each representing one of the segments of a 7-segment display. The decoder uses logic gates to convert the BCD input into the appropriate output for the display. Next. Figure 6, 7408 pinout, or the IC 7408 logic gate chip. Next. The 7408 IC is a logic gate that performs the Boolean function of AND. It has 4 input pins and 1 output pin. When all inputs are high, 1, the output will also be high. If any of the inputs are low than 0, the output will be low 0. It is commonly used in digital circuit design to perform logical operations and control circuits. Next. Figure 7, 7486 pinout, or the IC 7486 logic gate chip. Next. The 7486 IC is a quad 2-input exclusive OR gate, meaning it contains 4 individual logic gates that perform the exclusive OR operation on 2 input signals. This operation outputs a high signal if either of the inputs is high, but not if both inputs are high. The 7486 IC is commonly used in digital circuits for implementing Boolean functions and generating control signals.
So good day everyone. I am assigned to discuss our circuit diagram or circuit design. And Pauline will be discuss what happened after we transfer the circuit design or circuit diagram into PCB. So this circuit diagram is just only a simulation. So I'm gonna show you a demo. So this diagram, a circuit diagram, is a 2-bit multiplier or 2x2 binary multiplier. So itong dalawang 7-segment, let's say this is our input, and then this 7-segment is the output. So let's say this 7-segment is 1, and then the other one is 2. The output is 2 because this is a multiplier, so 1 times 2 equals 2. Let's say this one is 3 and then remain to this one. Then the output is 6. Since this is a binary, that's why we only have a 2 switch per seven segment for input. So let's try again another input. 3 times 3 is equals to 9. So, and on dalawang 7 segment, it only can display a 0 to 3. And then for the output, it can display 0 to 9. Since in 7 segment, 0 to 9 ang pwede lang ma-display. That's why our diagram is hanggang 3 lang yung kayang dapat i-display ng dalawang 7 segment. Kasi if ever na isa dito sa dalawang to is magpo-4, so lalagpas siya since isa lang yung 7 segment natin for output. Hindi niya madi-display yung right output. For example, if this is A4 and this is 3. That's why this 2 can only display 0 to 3. And that's all. Thank you. So good day everyone. I am assigned to discuss our circuit diagram or circuit design. And Pauline will be discuss what happened after we transfer the circuit design or circuit diagram into PCB. So this circuit diagram is just only a simulation. So I'm gonna show you a demo. So this diagram, a circuit diagram, is a 2-bit multiplier or 2x2 binary multiplier.
Here are the steps we've made to successfully fabricate our single-sided PCB. So after we finalize our PCB layout, we start the process by printing the design in a paper, cutting the PCB depending on the size of our printed design, and transferring the layout using an on. So the first step that we've done is cutting and transferring the layout. So adding baby oil to your plain paper PCB layout would allow more light to pass through during the photo exposure process. And then we clean the PCB afterwards to remove the oil. Next step is the PCB photo exposure. So we've used LED lamp in doing the exposure process, which has a recommended exposure time of 8 to 10 minutes. And for the next step, we develop the photo exposed PCB using the developing solution that comes from the percentized PCB pack. In doing this, we'll have to mix the solution with the tap water in order for it to work. And most often, you'll have to mix the granules with 500 ml or 1 liter of water. So in our case, we've used 1 liter of water. And we put the PCB in a container with a mixture, waited 5 to 10 minutes until the paint from the unmasked areas are dissolved, and then we wash the PCB in a running water after. And for the fourth step, we proceed to etching the PCB. So it is done by submerging the photo-developed PCB on the etching solution, which is, here we use ferric chloride. So we also need to agitate our tray and observe it until the unmasked areas are dissolved. It took us 25 to 30 minutes until we finished this process. So next step is the drilling the holes. So we use mini drill for this process and 0.3 mm as our drill bit. Drilling is done for the holes for the components. And for our last and final step, we solder the components. So a PCB layout usually comes with a parts placement diagram, and we follow it for mounting our components, then solder our component leads to the copper side of the PCB. And now, here is our done circuit, and here is our working circuit. So in general, a 2-bit binary multipliers are used in digital systems that require fast and accurate multiplication of binary numbers. They are commonly found in a wide range of applications, including scientific and engineering calculations, financial calculations, and computer systems. So that's all for our presentation. Thank you.